Welcome everyone. You are joining us for addressing spectral characterization challenges in the imaging and sensing industry, presented and hosted by Photonics Media. Today's speaker is Christopher Gordon, a senior scientist at Optronic Laboratories. Chris's background is in analytical and physical chemistry, and his graduate research focused on the development of laser-based chemical sensors utilizing laser-induced breakdown and Raman spectroscopies. In this webinar, Chris will address the critical role of spectral characterization in ensuring the performance and reliability of modern imaging and sensing platforms. Attendees will gain insights into the most challenging aspects of characterizing modern imaging platforms and the need for robust and reliable measurement data. A quick note, feel free to ask questions in the chat at any time. If you experience technical issues, try logging out and back in. You'll receive a link to the webinar recording in your inbox after this session. With that, let's welcome Chris Gordon.
Get my screen shared here. Okay, can you see it?
Yep, looks good.
All right, well, thank you very much, Haley. Again, my name is Chris Gordon. I'm one of the application scientists here at Optronic Laboratories. So my main job is interfacing between the technical group and Optronic Labs and the customer base, just to make sure that we can facilitate getting a system to meet their needs. So when I was given the opportunity to give this webinar, my main goal was really just to identify the main challenges that our customers have when they're characterizing sensors, and also address a lot of the questions that I typically get from the customers. Not to mention, sensors in general have become ubiquitous in our daily lives. So there are tons of different types of sensors, different architectures, and different international standards that exist. So I just wanted to kind of give a brief overview of all of those, and then ultimately provide kind of a practical approach to obtaining spectral measurement equipment. So I'll start just kind of with a really brief introduction of Optronic Labs, what we do generally, and then get kind of right into sensors, sensor materials, sensor types, and architectures. Very generalized, because essentially there are full courses that exist for different aspects of this entire talk. So hopefully can cover things in just the basics and of what you need to keep in mind when you approach making these types of measurements. I'll talk about some of the limitations in terms of like sensitivity and response for the sensor, and how that response can be non-uniform or uniform, which will lead us kind of naturally into the different calibration and measurement geometries, power response versus irradiance response. And then I'll have some time just to kind of show you the list of standards that exist for the different types of sensors, kind of give you an idea of within those standards, the different types of characteristics that you would measure for your sensor and characterize. And then again, like I mentioned, give a practical approach to obtaining instrumentation to complete those characterizations. And then if any time left over, some questions or clarifications that you guys might have. So Optronic Labs has been around since 1970. Some two former National Bureau of Standards scientists, which is now NIST, saw a need in the industry for relatively affordable optical standards, being relative to getting one directly from NIST or NPL or a similar organization. So they created their own optical standards, and then obviously needed measurement equipment to characterize those optical standards. So they started developing their own instrumentation, which has led to a variety of platforms: scanning versus non-scanning systems, broadband versus spectral, detector standards and optical standards, material standards. We've come a long way, but what we try to do is just keep improving the way that people measure light and have confidence in the characterizations they perform with our equipment. So one thing that I hope to not be redundant, because it's literally the title of the slide, but all detectors are not created equal. And just to kind of emphasize that point, I put a very busy plot up here, but just to explain what it is, on the y-axis is a metric called the specific detectivity. We usually just refer to it as D star. And what that is, what you can think of, it's a normalized metric that allows you to directly compare different materials, different sizes for different active areas, as well as different detection, electronic bandwidths. Those get normalized out so that you can compare the detectors directly. And this thing is plotted as a function of wavelength. And again, this looks like a relatively small scale, but just to point out a couple other items, the y scale is in orders of magnitude. So that's the logarithmic y-axis. Each one of these is 1 micron. So to give you an idea, between what is the 0 point on this scale and 1 on the y-axis, that small region holds all of your UV, vis, and near-infrared sensors that aren't shown on this plot, like your silicon carbide, your alkali PMTs, even your gallium arsenide PMTs. They're all in this region here, which is very tiny relative to the rest of the spectrum, which contains all of the infrared spectrum. So now you have an idea of what the axes are, and if you look in y-axis, you're looking decades rather than just small increments. If you look at what the two straight curved or exponential looking lines are, those are the theoretical max values for D star, essentially the ideal limit in terms of the detectivity that you can get for a photovoltaic or a photoconductive detector. And that's based on ideal noise scenario. In other words, you're limited by the actual noise of the measurement, like the shot noise of your detector, or particularly when you get into the infrared portion of the spectrum, thermal noise due to random generation and recombination of charge carriers. If that was the limiting noise factor, then these lines represent the maximum detectivity that you can achieve. And obviously they're all non-ideal cases because they involve pre-amplification electronics that have their own noise, photoconductive specifically, but also some photovoltaic can be operated with a DC external bias, and that circuitry has its own noise associated with it, particularly low frequency noise. So all of those things obviously keep D star values from being ideal. But one thing you can notice is that at the left-hand side of the plot, where all of the region I pointed out before, and then even into the shortwave infrared, 2 or 3 microns, you can get generally very responsive sensitivity. The D star values tend to be pretty high, and you have relatively low noise, which gives you the ability to get such higher D star values. But as you go into the infrared, particularly when you get into the mid-wave, which is kind of where the curve starts flattening out around 5 microns, and then out into the long wave infrared, the sensitivity decreases quite a bit. You're talking orders of magnitude less sensitive than your visible near-infrared sensor materials. Higher noise thresholds and lower energy band gaps where they absorb get closer and closer together, so you're very, very noise limited. So what you can see, the temperature values on here on the order of cryogenic operation in order to achieve sufficient sensitivity. Although nowadays, some of these are being offered in more of a TE cooled environment if you don't need as much sensitivity, but they definitely need to be cooled in order to be useful, particularly for radiometric purposes. So again, the max sensitivity you can achieve decreases with increasing wavelength. So when you get into the infrared portion, you have to be aware that inherently those materials are less sensitive than particularly what you might be used to in the visible in terms of their sensitivity. So that's one thing to keep in mind. Just to go over the general types of sensors, there's 2 main types, although there are 3 different types shown on that plot before. But the curved plots, all of these that have a peak and then drop off, they fall under one of 2 categories, either a photovoltaic sensor or a photoconductive sensor. The third type functions on a different physical process, which is essentially temperature changes when photons impact on the blackened material, and they're small temperature changes. So they tend to not be very sensitive. But one thing you'll notice, all of these flat lines across the bottom, while they might not be sensitive, they respond equally, essentially equally, over very broad spectral ranges, from the visible all the way out into the far infrared. So what they lack in sensitivity, they make up for in coverage. But the two main types, first of all, photovoltaic. As the name implies, a photon produces charge carriers, which generates a voltage, which can then be read out as a current. So that's your standard typical, like your PN junction or PIN junction photodiodes. They tend to be very well suited for DC detection, which electronically is a lot easier because they tend to be very sensitive, as you can see, remember from that previous plot. They tend to have very low noise. They tend to be shock noise limited and not thermal. So you can tend to use them at room temperature, or you can even heat them slightly to keep them thermally stabilized, and you can still get really good sensitivity. But they only generally operate from the UV to the NIR, although obviously there are some ways or some applications where you can use like a mercury cadmium telluride in photovoltaic mode versus photoconductive. But generally speaking, most of your photovoltaic cells are UV vis, NIR, into maybe the SWIR region, 2 or 3 microns. Photoconductive is a different animal altogether. So the name implies photo means that light gets absorbed, but it doesn't produce charge carriers like photovoltaic does. What it does is when charge carriers are produced, it changes the conductivity. So these are operated by applying an external DC bias, a voltage across the detectors. Just off the top, I think like your lead salt detectors, for instance, maybe several volts, 6 or so maybe volts. For your MERCADs, you're typically looking more on 10 or more volts. But what this does is it produces a DC current across the detector at all times. So you have a DC current that might be on the order of tens of milliamps. When that photon is incident on the surface, the conductivity of the material changes, and therefore you'll get a change in current. The issue with these types of detectors is that the current that you're measuring might be nano or microamps, and that small current is sitting on top of tens of milliamps, so orders of magnitude higher or larger DC background signal. So these detectors need to be operated, or generally operated, if you want decent sensitivity in AC detection. And generally what that means is you have a mechanical chopper, which will actually block and unblock your signal at a fixed frequency. And what that does is then allows that current that's on top of your DC current becomes now a small AC current that's oscillating at a fixed frequency. And then you can have electronics that lock into that frequency and essentially ignore everything that's the DC or low frequency component. It takes your optical signal up to a much higher frequency that's hopefully a more noise-free version or region of the noise spectrum. And they can operate from the visible all the way out to the far infrared. And I mentioned thermal sensors. They, again, much lower sensitivity, but they don't operate on the principle of a band gap and absorbing the photon, promoting and generating the charge carrier. So you get a small signal, requires AC detection like photoconductive does, but you get a very flat response over a very wide spectral region. So, I mean, those in general inherently imply or impose not necessarily limitations on different detector types, but what you as the manufacturer of either a detector or sensor or device need to be aware of is the type of sensor you're using, the region that you're using it in, because they all have implications when it comes to the detector sensitivity. In terms of architecture, they generally fall into 2 main categories, either a single element sensor, which is literally just one one detector element, you can think of it as just one individual pixel and one signal channel. Very useful in broadband sensors or in detection ranging measurements or applications where you're just concerned about the intensity of the light. You can also use them when you're making spectral measurements, but because there's one detector element, that requires you to have the mechanical means to take the optical signal and physically scan it across the one detector element. So when you heard me refer to as scanning systems earlier, that would employ something like one of these single element detectors. You can put multiple elements in multiple pixels together in a detector array. And again, most of those are either a linear array, which is just a one-dimensional array of pixels like this bottom chip here that you see. And they're very useful in smaller, compact, non-moving monochrometers or spectroradiometers. Also used in multi or hyperspectral imagers where you have an image of a slit that gets physically scanned across a sensor. So essentially you're just scanning your entrance slit for your hyperspectral imager, push broom method across this linear array. Most sensors now, in terms of specifically when it comes to imaging, use what we call a 2D array, which is literally just a two-dimensional array where you not only put pixels in a line, but you stack them in the second direction as well. So you have a two-dimensional array where you can actually form images if you have an imaging system, or you can take spectral measurements and utilize different portions of the chip to maximize your signal to noise ratio. Obviously, since you have multiple elements, detector elements, with each one having essentially its own signal output, the electronics and programmable logic that are needed to accurately read out the signals from these chips are much more complicated and involved. But obviously, you get a lot more versatility and a lot more information using an array versus a single element detector. Okay, so we mentioned sensitivity, but one of the aspects of sensor performance that goes kind of widely unnoticed and we get a lot of questions about is how the sensor responds uniformly or non-uniformly across its entire physical active area. And I have kind of the two extremes here just to kind of show you how much it can vary. But what I have here is a two-dimensional plot of the normalized signal from a silicon photodiode. It's a 10 millimeter by 10 millimeter square photodiode. And we have a small half a millimeter diameter spot operating at 550 nanometers or green spot. And it literally make measurements by walking that small spot across the surface of the detector element and then compare how that signal changes with physical distance. And what you can see is, first, it's really flat. We're not really looking at it from the side view because it's a 3D plot, but just looking at it, it's very flat. You only see deviations really as you get to the very edge of the sensor. And that's very typical for sensors. But one thing for silicon specifically I want to point out is that this y-axis, which is your normalized signal, is the increments are in tenths of a %. So while if you just look at this plot at the edge, it looks like it falls off a cliff, that cliff might span a couple tenths of a % in signal differences. So it's a very highly uniform sensor material, and it's very well known in the industry for being a very uniform sensor material, which makes it a very good, one aspect of it that makes it a very good absolute reference material. It also has incredibly low noise. You're thinking on the order of picoamps or less, femtoamps. It's definitely going to be limited not by the sensor material, but your electronic noise. So it's a really good standard, very highly uniform. So that inherently tells you that you can have quite good confidence if you have a measurement spot that underfills this detector. No matter where you make that measurement, it's going to be within a couple tenths of a %, which is very good reproducibility, very good confidence in your measurements. Now, on the other end of the spectrum, that was not meant to be a pun, but we have a lead sulfide detector. And your lead salt detectors are photoconductive, and they work generally in the SWIR and mid-wave infrared. Again, they're known for not being uniform, particularly when you compare them to silicon. So this is a 3 millimeter by 3 millimeter PBS or lead sulfide detector. And we're using a different wavelength here. This is in the SWIR in 1500 nanometers. But we use the same spot size, a 0.5 millimeter spot, and see how the signal changes as you walk it across the 3 by 3 millimeter squared detector element. Obviously, the plot looks distinctly different from silicon, which was very flat. But interestingly enough, it's more sensitive, and it's not sensitive just in the center of the element. It's not like a Gaussian peak where it falls off on either, as you move away from the center. The midline material is where you see the highest sensitivity, and it falls off as you go away from the midline. And unlike silicon, if you look at the y-axis for this plot, this normalized plot, the increments are in 10% increments. So if you have a small spot and you're trying to quantify the amount of radiant power in that spot, if you make the measurement at the midline of the sensor versus towards the edge, now you're talking differences that could be 50 or 60% different. Okay, so that inherently imposes some limitations on how we can deal with this detector versus silicon, or as we'll see in a moment here, if you need to overlap spectra from different detectors, this knowledge is very important when you're making those decisions. Okay. So this geometry that I've been kind of mentioning in the last couple of slides, where you have a small spot, and that spot underfills the active area of your sensor, that's referred to as a power response measurement. If in those previous cases, if those sensors were calibrated detectors and they were calibrated for power response, we could actually quantify the amount of radiant flux or radiant power in terms of watts using those two sensors. But the responsivity difference and uniformity difference that we just discussed, obviously we need to take that into account. So if you're making this measurement with silicon, we already showed, and we know that silicon is a very highly uniform sensor, and that power that you measure, it's going to be correct. It's going to be correctly measured no matter essentially where on the sensor surface you're irradiating, and at different spot sizes. It'll be insensitive to spot sizes, provided that the spot is underfilling the sensor area. Again, that's one of the reasons why silicon is used in the industry as an incredible absolute standard reference detector material. But if we're trying to measure the same size spot with the lead sulfide sensor, obviously we're going to see drastically different outputs from the detector given the same spot size if we move it from point to point on the sensor. And we mentioned that could be tens of % difference, which means if you're using this lead sulfide sensor as a calibrated reference standard, the calibration that you do or the measurement that you perform with it needs to be the exact same spot size and location that was used when the sensor was calibrated. Because if you deviate or change either one of those parameters, you're going to change the signal given out by the detector because of that non-uniformity difference. Which means the alignment then becomes incredibly crucial when you're making power measurements with these detectors. Kind of what that kind of looks like in practice. I have a plot here that's the measured reflectance off of a detector surface or a sensor surface measured with 3 different detectors. The blue plot here is the reflectance measured with a silicon detector. The gray plot is with a germanium detector, which is responsive from 700 up to about 1700, 1800 nanometers. And then the lead sulfide detector. So we have the 2 detectors that we referred to and compared in previous slides, making the same measurement, obviously in different spectral regions. So 2 things. One, we need to be aware that we're using 3 different detector materials. And the first thing we need to be aware of is the relative sensitivities of those detectors, and also what we had just discussed, we need to be aware of the uniformity of those different detector types, which one is the most uniform and which other ones, obviously which is the least uniform, but knowing which is the most uniform helps guide you to figure out how you process this data. So just looking at this screen, there's a couple things, or looking at the plot, there's a couple things you notice when you look at just silicon and germanium overlap. The shape of the plot looks really good. They're offset just a little bit. This is a linear plot, not a logarithmic plot. So that's a tiny little offset, which means that you can infer that germanium is fairly uniform, maybe not as uniform as silicon. But you do see some deviations. At the very bottom of the germanium plot, it rises a little bit more away from the silicon. And if you look at the other end, the silicon at the end of its measurement rises up away from the germanium. And that's because another thing, you need to be aware not only of the overall sensitivity of your sensor, the spectral sensitivity of your sensor. So these are the normalized responses for these three detectors. Where you see those deviations, particularly I'll use the silicon where the blue plot rises up away from the gray plot there as an example. That's occurring between 900 and 1100 nanometers. Well, if you look at the blue response plot for silicon, that's where the response of silicon is falling off a cliff. I mean, you get very large changes in response with small wavelength differences. And oftentimes in a scanning system or a dispersive system that uses a grating, that might also be the edge of the grating response, which can help to compound that error. So you'll start to see at the edges of responses some deviations, which means you need to know where that happens so that you're not using those specific regions of the measurement to make decisions or to overlap or to scale or things like that. So germanium silicon, very similar, slight offset, but obviously when you look at the red plot, which is the lead sulfide, a couple differences. Obviously, it shifted completely away from the germanium. Not necessarily that surprising. We know that you can get quite a bit of shift in measurement or response depending on where you're making the measurement. And this is reflectance. So this, 20 to 25%, you're talking, less than 10%. So these are huge differences radiometrically, but we're not talking, it's less than an order of magnitude. So obviously we're going to need to scale that plot. But the other thing that you can see is the little box function here. It's sloping up for lead sulfide and it's sloping down for germanium. So then you need to look at that and say, which one do I have more confidence in? Well, I can look at that germanium and say, well, that box feature is right around 1300 nanometers for germanium. That's where germanium responds pretty high. It's almost towards the peak response, which is close to 100 nanometers. But for lead sulfide, 1200 nanometers, right towards the very end of the low end of its response. So in that specific region, I need to be aware that I'm comparing a more responsive germanium spectral region to a much less sensitive lead sulfide region. I don't want to do the overlap there. I had the confidence in the germanium there. So what you can do with all that is make the appropriate decisions in terms of scaling all of your less uniform sensor measurements to your most uniform sensor. So scale the germanium a little bit so that it overlaps perfectly. Scale the PBS down in a region where you're not looking at a drop off of germanium and you're not looking at a low sensitive region of PBS. So maybe in the 1600 region before germanium falls off a cliff. Those decisions need to be made based on knowledge and understanding of your sensor material, your sensor architecture, and the response. So it's not straightforward. It's not all detectors, again, are created equal, and you need to be very wary of anybody that suggests that you have a system where you can just plug in a detector and it spits out results without doing any thinking and processing of the data. So just keep that in mind. To do this correctly, it does take practice and an understanding of the sensors that you're working with. Oh, too many mouse clicks there. Okay, so this, again, this geometry, this power response geometry, how it's done experimentally. What I've shown here is kind of just the inner workings of a collimator, where at the top here I have a collection, an off-axis parabolic mirror that collects the radiant flux out of a monochromator, for instance, and creates a collimated beam. One way that you can do power response is by using an aperture. That aperture is the beam size down to a spot that underfills your detector. Another way that you could do that is by using a second OAP in this bottom position and maybe focus back down to a small spot. Obviously, that'll give you more flux to measure and a higher signal. But one thing that I want to kind of emphasize as you're going through here is when you're looking for measurement equipment, try to identify accessories or components that can pull double duty and multitask. It's a way of kind of stretching your dollar by giving yourself the ability to do more than one measurement type using the same equipment or most of the same equipment. So just to emphasize that, I've shown here that you can use a collimator and use an aperture, signal limiting, obviously, down to a small spot. And I obviously made it very small here just to emphasize the reducing of the size. But once you have a small spot that's small enough to underfill both your reference detector as well as your test detector, you'll bring in your calibrated reference standard, which I've just, for an example, our 750 series detector head and preamp combo. That's calibrated for power response. You bring that in, align it so that you're underfilling the sensor, and then you measure the radiant power that's present in that beam. And once that radiant power, you'll do this obviously spectrally, walking through the spectral intervals and measure the radiant power at each increment. And that'll give you the spectral radiant power, spectral radiant flux that's present in that beam. Remove your reference sensor and substitute in your test sensor. I just showed a simple TO can here. So what you'll have then is the spectral measured signal from your test sensor. That'll be in amps or volts. And that'll be as a function of the known spectral radiant flux. So this measurement will give you the test sensor's response in either amps per watt or volts per watt. So obviously I have a small spot here, maybe not as small in practical purposes, but for power response, you're underfilling the sensor. And as we mentioned, that can be a problem when you have sensors, whether it's reference standards or test sensors that are non-uniform or are known to suffer from non-uniformity. Because when different detectors, especially if you have a reference sensor and then a test sensor that's a focal plane array, that's an imager, that's a full camera device, they obviously have different physical specifications. They take up different amounts of space. They obviously will require, for the most part, different mounts, fixtures, and positioning and alignment equipment. And every time you substitute out a detector, it needs to be positioned and aligned meticulously, and I mean correctly. Obviously, that can be a very time-consuming when it comes to actually doing this in practice. So one thing that you can do to kind of alleviate that redundant alignment is employing what we call transfer calibrations to help save some time. And just to show you kind of how that's done in practice, it starts out the same way by measuring the radiant power in the original position using a calibrated reference standard. And once the power in the beam is known at this position, you can introduce, say, like a flipping mirror that can flip into and out of the beam path to physically move the beam to a different or auxiliary position. Once it's directed this way, you can either use the same reference standard as before, or maybe a different auxiliary or working standard detector, and measure now the radiant power that's in this auxiliary position. considering that you've measured the flux in the original and auxiliary position, you now have essentially transfer values is how we discuss this in practice. This position is referred to as a transfer calibration. In other words, you have knowledge in this position of what the radiant power is in the original position. And the nice thing is for doing this is that once you have the detector in this auxiliary position, you can keep it there. You don't need to take it out and remove and replace it or substitute it with the test sensor. This can stay in this auxiliary position. And then the calibration that's done in this original position, you can now do that using the transfer calibrations or the ratios from the transfer to the original to make alignment easier and not have to align the reference standard each time. So that's one thing. Obviously, space-wise, this is kind of compact. I did it just to fit it on a slide. These measurements will require things like careful control of room lights and baffling where baffling is possible. These accessories might have built-in baffling, for instance, to control the radiant flux and minimize any sort of background and stray light. But physically, this shows you the orientation of the detectors and how they're used in this type of calibration. So that's power response. For either non-uniform detectors like your lead detectors or your lead salt detectors, or sensor elements that are, sub-millimeter on the order of maybe several hundred microns, and you don't have an accessory with optic quality capable enough of producing a spot size small enough to underfill your sensor. The other geometry, instead of underfilling the sensor, is done by overfilling the sensor. And if you have a spot and you're overfilling an active area of the sensor, just pictorially, kind of if you're looking at the silicon on the left and the lead sulfide on the right, now these detectors are only going to respond as a result of the radiant power that's on the active area itself. Any flux that's outside of the active area is not going to produce a measurable electrical signal. So you'll have what's actually quantified then is only the radiant flux power in watts over this active area, which will be in units of square centimeters or square meters. And watts per unit area is what we call irradiance, is the watts per centimeter squared typically, or watts per meter squared. Provided that you have a really uniform spot, we're talking, plus or minus a % uniformity is considered really good. Larger beams might not be as uniform, but provided that the spot uniformity is within an acceptable limit, you can, the detector signal that you're seeing is the average over the entire active surface area. So if you move a uniform spot, you'll still get the same average output. So this geometry is much less sensitive to positional alignment as a power response measurement. So that's another thing. If it's either impossible for a small reference standard sensor active area, or you have a really non-uniform detector in a particular region, you can perform an irradiance response to get a reliable shape or signal, the spectral shape of the response. And then there are some ways that you can maybe apply your knowledge of the active area, if you know that precisely, or if you put an aperture over the sensor area to which you know the diameter accurately and precisely, I should say, you can calculate within a certain uncertainty what the power is that's measured. But it gives you a way to give you a more reliable and reproducible signal for either uniform or incredibly small active areas. So those are your two main calibration geometries. The irradiance itself is done the same way via substitution that the power response measurements are performed, but in this case, you're using a larger beam that's overfilling both sensors. You'll bring in a sensor that's calibrated, this time for irradiance response, to measure the irradiance of the uniform beam. And then once that irradiance is known, you substitute out with your test sensor also being overfilled. And then the signal that's provided for the known irradiance will give you these test sensors irradiance response, which will then be instead of amps per watt or volts per watt, be an amps per watt per centimeter squared, or volts per unit of irradiance, watts per centimeter squared. Okay. So those are the main geometries, physically how those measurements are accomplished in practice. The other thing that's becoming not more of an issue, but obviously sensor technology, ever since transistors and diodes where solid state materials have been developed, have just been technologically taking off exponentially. The architectures are improving, detector materials are improving. You get a lot of different types of sensors, and then you get national and international standards that try to normalize the types of metrics that are relevant to different detectors, so that you can do these measurements and perform these characterizations and then compare them from one sensor or one imager to another, even if they work on different principles or they have different structures. A lot, particularly in my mind, what I'm thinking of is the most recent IEEE standard, the 4001 for multi and hyperspectral imagers. The types of architectures that exist in those sensors vary quite a bit, both in how they operate, the types of signals and dispersion elements that are used. But this does a really good job. They made a concerted effort to develop performance metrics that are capable of being measured using lab equipment, R&D equipment, like monochrometers and calibrated sensors that are available to most people, but that can be relevant and compared across those different architectures. I've highlighted the three the standards that I've encountered the most frequently. For single element sensors, it's the ASTM standard, E1021. Imaging sensors, off the top of my head, I think this is for IR imaging sensors as well, but I'll have to go back and look. The EMVA standard 1288. And then, as I mentioned, the relatively new, I think it came out in 2025, the IEEE 4001 standard for multispectral and hyperspectral imagers. So even just based on the type of sensor architecture you have, there could be more than one standard that could apply. So one of the things, particularly for manufacturing, is be aware of which particular standards your customers require that the device or product be adhering to, because these standards will specifically tell you in detail the type of measurement equipment that you need, the physical geometries and relative orientations that the light source and sensor need to be at. So it does provide a lot of really helpful information to help guide you to making these characterizations so that you can do them correctly. But just identifying the specific standard is usually not enough, because once you get into these standards, you'll see that there are various performance characteristics that need to be evaluated. We refer to as different measurands. Like, for instance, we've been essentially at this point with power response and irradiance response been talking about the spectral responsivity measurements, characterizing how your sensor or device responds spectrally. But on top of that, you'll also need to, depending on the application, all applications will likely require that you identify and ensure that the sensor or architecture you're using has sufficient linearity. In other words, that the signal responds linearly with optical signal. And there are ways and methods in the standards that describe how those measurements are made as well. In order to figure out how sensitive your detector is, part of that is characterizing the noise of your detector. I know specifically for the 1288 and the 4001 standard, there's more measurands that are covered, things like both response uniformity as well as the spatial resolution. If you have small pixel sizes and you're measuring a large field of view of a I don't know, a crop that you're trying to identify good versus poor plant crops. You need to know that what each pixel represents in terms of the physical space in that image. So you need to, additionally to the spectral response, characterize the spatial resolution. Thermal sensitivity, particularly in IR-based sensors in the infrared regions. Thermal control is of utmost importance. So these standards are packed, and they can be very daunting when you first look at them. But just what you need to be aware of is when you're approaching a particular application, you do need to know, again, what is the specific standard that's going to apply to your device? And then when it comes to your specific device, one, where in the spectral region are you? Are you in a really high sensitivity, low noise region like the VIS, NIR, maybe into the SWIR? Or are you already in a position where you're in the mid wave or a long wave doing thermal imaging, where sensitivity is low, thermal background is high, so your sensitivity is decreased? You need to know those things about the materials and architectures that you're working with. In addition to just measuring these different measurands or performance metrics, different standards may also require that you illuminate your sensor in different ways. I don't think this, off the top of my head, applies to the 1021 single element sensors. I think it's been a while since I looked at that, but I thought that just dealt with power and irradiance response. But particularly with focal plane arrays, imagers, and hyper and multispectral imagers, in addition to a collimated source, you may also need what's referred to as a Lambertian source, where instead of having your light collected by a collimating optic and put into a parallel beam, you need that illumination to be what's referred to as Lambertian, or it's coming out in a full hemispheric, 2 pi stir radians, where the intensity follows the cosine law, and instead of a collimating optic, instead what you can use is something referred to like as an integrating sphere, which is just literally a spherical accessory that's coated on the inside with a very highly diffuse reflective material, like a PTFE for the UV vis, NIR, and into the SWIR. If you go beyond the SWIR, that's no longer reflective, and you need like a diffuse gold coating. And a gold coating you can probably use down to at least 900 nanometers, if not lower, all the way out to the far infrared. So again, this might seem like 2 different system configurations that you would need if that's something you need to do. But one thing that I want to mention is that the only thing that's different in these 2 setups is the output or the exit accessory. A collimator on the collimated flux versus a integrating sphere to provide Lambertian illumination. The core spectroradiometer, or the core monochrometer and light source is the same for both of these things. So just looking at this, even though you have 2 different means that you need to illuminate your sensor or your device in order to characterize it, you can do that using the same core system and just changing the exit optic or the exit accessory. Additionally, anywhere that you can include modularity in your system, that helps to facilitate the system being more functional. So for instance, if you in the monochrometers, what looks like a blackened CD, that's a tri-grading turret. So it's actually a turret that's got 3 you can add up to 3 different diffraction gratings, and that provides versatility in that you can use the same monochrometer and have interchangeable gratings that will allow you to cover the entire optical spectrum with 2 or 3 different turrets. Or if you want more control within one spectral range, you can have multiple gratings that cover the same spectral range, but at different groove densities. So that gives you different wavelength resolution for your measurements. That comes with trade-offs in terms of signal and such, but it allows you to be much more versatile. And for the source attachment I have shown here is for Optronic Labs is our single source. It's just got a little stuff to see, but it's a little quartz tungsten halogen bulb, my filament bulb. But what we also offer are dual source attachments, which in addition to the QTH bulb here, you can pair that with a second source. So you can include a deuterium lamp if you want to go all the way down deeper into the UV, because quartz tungsten halogen really falls off a cliff after the visible. Or if you're measuring in the infrared, you can pair the QTH bulb with an IR glower. That'll give you flux beyond, the thermal flux that you get from the QTH bulb. And you can do that with a very quick optic that flips back and forth, so that doesn't require very controlled and precise alignment each time. Though all of those things together give you real versatility in a core system, give you the ability to change the output optic in order to accomplish different materials. So this is for spectral or, quote, monochromatic illumination. I put quotes there just because you need to know that these spectral systems they're not lasers. They don't put out a finite wavelength. Based on how they're configured, the grading, the apertures that you have, the slit widths and things like that, that'll define a range of wavelengths that are allowed out of the monochromator. And I call that the system bandpass, or the spectral bandwidth. So this is how, if you need to illuminate to characterize your sensor spectrally. Some standards, off the top of my head, I can think of, if you have a solar cell, and in addition to just characterizing its spectral response, that spectral response also needs to be characterized when it's measuring the monochromatic light in the presence of a broadband background source. Obviously, if you're thinking of a solar cell out in the sun, even at the wavelengths the solar cell doesn't respond to, it's getting bombarded with broadband illumination from the sun. So if you're measuring, for instance, or characterizing the external quantum efficiency of a solar cell, you'll have a setup where you have something like this collimated bias light source, where you can have a tungsten bulb, and you can kind of tune that to be at, say you want it to be a certain color temperature, like luminant A. You can adjust the current so that the output is really close within a certain acceptable uncertainty, and then just have that bias light source on your device as you spectrally calibrate to see what the effect of having a bias supply has on your sensor. And again, you can bias it either with a collimated focused beam, if you have a collimation or a focusing lens as your output, or again, you can throw an integrating sphere after a light source and get good uniform Lambertian illumination. So yeah, it seems very daunting when you get into one of these areas, especially if you've never done sensor characterization before. There's guidance out there, but I just really want, in terms of takeaways from this, and to keep in mind when you get into a project like this, is one, you really do need to understand the behavior of your specific sensor type and or architecture. You might be working with a very uniform sensor, and that may not be an issue, but for instance, you're trying to make absolute measurements in the infrared that we've discussed are kind of historically known for some of these limitations in non-uniformity and low sensitivity, high noise. So if you're trying to quantify something and have some confidence in that, you might want to tie that measurement back to an absolute measurement made with like a silicon sensor, that you have a lot more confidence in the absolute output of the measurement of the absolute signal. So do the background work. And again, if you're used to working, maybe you've worked with sensors, but you're only used to working in the visible, and then you're trying to move into the midwave. That is a whole other beast with whole other limits of sensitivity. On top of that, again, as I mentioned, in those longer wave infrared regions, the background in the room, just based on the temperature of the room, emit radiation in those regions. So you're fighting a lot of things in the infrared, and that's stuff you need to be aware of when you're embarking on one of these projects. Again, as I mentioned in a couple slides ago, make sure you're aware of the standard that applies to your specific device, and or the standard or specs or standard or standards that your customers may require the device to adhere to. Those obviously will guide which standard or standards you're following for your characterization. And I know budget is always a limitation. I certainly understand that. But if the main takeaway when it comes to instrumentation, specifically when it comes to radiometric instrumentation and budgets, the very first place you want to look to save money is don't sacrifice quality of the instrumentation just to save money up front, because that leads to a lot of issues down the line in cross-referencing measurements, trying to figure out where the issue is, maybe even having somebody else need to do the same characterization compared to it leads to a lot of issues. So everybody does need to save money, but what I would highly recommend and encourage is that the first spot you look for a system that's got as much modularity as capable without sacrificing performance. But identify system components that are versatile, serve double duty, and you can use for more than one purpose. It's better to be in a situation like that. And like, for instance, if you have a collimator where you use that same collimator, you want to do power response, so you put an aperture in, you're going to have lower signal. And obviously that measurement will be done with less sensitivity. But you'll have the tube high quality. You didn't sacrifice on equipment and the quality of the optics, for instance, that are used, and the all of the mechanics that go into the instrumentation. Down the line, you may want to find a better way to do the power if you're suffering your detector has low sensitivity and a smaller spot is not feasible. But those are things that can always be added down the line while you're still making good, high quality characterizations and measurements. So that's really what I wanted to put. It can be daunting when you look at this stuff for the first time, particularly once you identify a standard and you start reading through it. But just be aware of what you're getting, what you're going to be dealing with your sensor, the standards that are relevant to you and your customers, and then save as much as you can by identifying multitasking equipment and accessories before you start needing to compromise on quality. So those are my main takeaways. I guess now if you've submitted questions, or if you have submitted them and want to come up with questions later and you want to ask me, you can feel free to email me directly. As far as I know, we'll get the inquiries from everybody and respond to them as well.